Good day, everybody. I'm very glad to be participating in the 2020 International Smart Cities Forum. My name is Magesh Chandramouli. I'm a faculty member in computer graphics at Purdue Northwest. Today's presentation, I'll be focusing on planning and design using the integration of virtual reality with genetic algorithm-based optimization. We will be looking at a final interface like what we see here, where the land use planning scenarios are developed initially using multi-objective optimization driven by genetic algorithms, and subsequently where virtual reality visualization is used to visualize some of the Pareto optimal plans. As we are aware, around the world, managing cities is becoming increasingly complex because of the geometric increase in population in the face of limited resources. So land use planners and administrators are faced with the challenge of having to manage these limited resources optimally for sustainable land use management. Virtual planning has several advantages. With virtual reality and 3D modeling, the land use planners can hold discussions and interact at the comfort of their office while they can still visualize land use scenarios, alternative land use scenarios, and potential optimal future land use scenarios. With visualization, they are able to get a better idea of the planning scenarios and make informed decisions. And in this study that we are going to see, genetic algorithm-based multi-objective optimization was applied to the study area, and the results were presented in the form of virtual reality-based interactive visualization scenarios where the planners can see and also make changes to the proposed designs. So there are two important steps. One is the multi-objective optimization based on genetic algorithms, followed by the visualization using virtual reality. And in this particular case, the multi-objective optimization considered enhancing three important objectives, namely maximization of green space and maximization of public service space and increasing the housing capacity. Let's take a quick look at the background from the virtual reality side. So with virtual reality, there are different kinds of options that are available, including desktop virtual reality, augmented virtual reality, and immersive virtual reality. So with the different modalities that are available, there are varying degrees of immersion and navigation that are provided. So with respect to urban planning, the planners and decision makers in a specific urban problem will decide which is the most cost-effective and efficient way to attain their goals in that specific problem scenario. With urban planning, there are many different types of data sets that are involved, including the shapefiles, the vector graphics, digital elevation models, TIN models, in addition to the 3D generated models of the buildings composing the cities and various other infrastructure components involved in a typical city. So all these formats need to be imported into the virtual reality scenario in order for creating the interactive 3D visualization. So with that background on virtual reality, let's now look at the genetic algorithm component. Typically with genetic algorithm, there are two important aspects. One is called selection, the other one is variation, very similar to how the evolutionary process works within a human population. And genetic algorithms are versatile search algorithms, and they are able to overcome the limitations of the linear programming methods, and they are able to provide a global optimum because of their ability to handle multi-objective problems with conflicting objectives, and also their ability to handle very large search spaces. So in this case, as you can see, the image of the genotype on the bottom left shows the representation of the land use or the phenotype shown immediately to the right of it. So the land use type, as you can see from the table, is divided into different components and different elements which are allocated different land use codes. And for the sake of the genetic algorithm, these are given integer based representations ranging from 0 to 9 for 10 specifically identified land use categories. And as mentioned earlier, the three objectives involve the maximization of the green space, per capita public service space, and the housing density. So first, the starting generation needs to be created for the genetic algorithm. So how is the feasible set created for this? In order for a plan or a genotype to be considered as feasible, it needs to satisfy some of the minimum criteria, such as a basic threshold of green space and a minimum number of housing units and a basic threshold of public service space. So every plan that's randomly generated is checked to see if this plan is feasible, if it satisfies these criteria. And because this is a randomly generated plan, millions of plans need to be generated to identify 100 plans for the first generation. And every plan is compared with other plans in each generation, and the values are calculated for the fitness using the fitness formula shown. So if a plan is to be included for the next generation, it needs to be compared with all the other plans within the same generation based on the fitness criteria explained here. And then the next generation is created in a manner very similar to the process of natural selection, where the number of genotypes retained from the existing generation is equal to the number of the total genotypes multiplied by the selection rate. So in this case, the selection rate of 20% was applied, as you can see, and then the processes of crossover or mating combined with mutation are applied to create the plants for the next generation. And once these plants are created, next we go to the virtual reality component, where a hierarchical scene structure used for defining the scene. As we saw in an earlier slide, there are many different components within an urban infrastructure setting. These include buildings, triangulation models, digital elevation models, raster data, vector data, and many other kinds of shapefiles and other kinds of infrastructure data too. So all these are organized as a hierarchical structure for defining the scene. So all these need to be first generated, and they are stored in a library that we will see shortly in the results and discussion. And to give a general idea of the software that were used, X3D, Unity platform, Java 3D, and scripting were used for generating these 3D worlds. And for the hardware component, the specifications are mentioned in the slide here. We used Razer Hydra, Microsoft Kinect, and HP graphics workstation along with HTC Vive for the VR based visualization. So as you can see here, this allows us to interact with the 3D models, and the scenes are created by putting together the various different 3D formats, importing them into the virtual scenario, and then using Oculus and HTC Vive, they can be interacted with. And from the results, it's evident that the genetic algorithm was performing pretty well based on the percentage of the Pareto plants in the final generation as compared to the initial generation, and also based on the total time for execution of the genetic algorithm. So from these, 2 Pareto plants are selected for visualization, and now we will see how these Pareto optimal plants are used for the visual comparison. So typically before this, when the genetic algorithm based plans are generated, there is a lot of information that tends to be abstract, that the planners and the administrators have to imagine or have to discuss with a lot of uncertainty. But with the visualization, the planners and the administrators are able to clearly see what exactly is the land use scenario that is being represented by the genotype. So this gives them a very clear advantage by reducing the abstraction and thus helping them with the decision-making process with less ambiguity. So the different elements, including the buildings and the other elements of the urban infrastructure, are added to the virtual world, as you can see here. And then the 3D virtual world thus generated can be navigated and can be interacted with. Changes can be made, and these are accomplished using the software and the hardware components mentioned earlier. So with the virtual plants, we have several advantages. Some of the most important including varying levels of detail and being able to see from multiple points of view, which offer a better insight in evaluating the different scenarios. So these results are organized and presented through an interface where the virtual objects shows it's a library of all the objects generated. All these objects, including the individual objects such as the houses, buildings, DEM models, tin models, etc., are all stored in the library here, and they can be used in multiple plants as required. So it is clearly evident that this kind of visualization offers a better way to navigate through, interact with the scenes, and identify the strengths and weaknesses of each scenario. So you can clearly see that with one of the Pareto plants, the green spaces are much easily accessible to the public for any selected urban area, whereas the other plan shows the weaknesses in being that the houses are kind of densely packed and are not providing enough access to green spaces to the public. So this is just one example of how these can show the strengths and weaknesses in a much clearer way. So on the whole, with the ability to visualize with VR being combined with genetic algorithm based optimization, there is tremendous potential in the planning and design of virtual cities. I'd like to thank you all very much for listening. Wish you a good day.